couple of applications of the derivative. That was in the area of the Taylor series and stationary points and related optimization problems. And today we're going to look at another two applications. The other two applications that we have here, which is curve sketching and kinematics. And we'll look at these two today. And that will more or less finish off the continuity and differentiation chapter for us. But we'll do more work with it. I think we'll do more work with some of the problems in the tutorials this week, and maybe in one of the sessions next week. Now, curve sketching used to be a kind of bigger emphasis and a bigger, more important idea in the past when we didn't have the tools we have nowadays, such as mathematical software, computer systems, or graphing calculators. Okay? So normally, if we're faced with a function and we want to have a picture of the graph of the function, we can very easily just ask MATLAB or other equivalent mathematical software to produce such a graph. But people did produce fairly accurate graphs of functions before they had these tools, and it's still worth looking at some of the techniques they use. They still are interesting techniques to see, and they are interesting. You know, they're the important. They pick out the important features of the function, and you know, still are techniques that we can fall back on when reasoning about functions or solving problems related to it. Okay? So the task might be, when faced with a function like this, so this is what we've been calling a rational function. So this is 3x squared minus 7 over 2x plus 1, is to know what the graph of that function might look like. Okay? And there are a number, in no particular order, but roughly going from, you know, first to last, there are a number of features of the function that we can pick out just from a careful consideration of the defining formula of the function. And these can help us to produce a somewhat accurate sketch of the graph of this function. So first of all is to think about what the domain of the function might be. So we're taking that these are real valued functions defined on the real numbers, or maybe some restricted subset of the real numbers. So you look at this kind of formula and you ask yourself, well, is that a well-defined, does that define some well-defined value for all real values of x? And it does for most real values of x, but there is a slight issue to be worried about, which is when you might get a zero expression in the denominator, that won't give you a valid value. And so that can point to something about the function. Okay? So we'll say more about that now shortly when we come on to look at this example in detail. So the following on from that, if you do identify any problematic points in the domain where the function won't be defined, is to see if you can figure out how the function is behaving close to those problem points, or how the function behaves as you converge to those problem points from either side. Okay? Now, typically, especially when it's because that problem of zeros in the denominator, it will be because the function is getting larger and larger, either in the positive sense or the negative sense. So it's tending to plus or minus infinity. So if you can deduce that, that is good, and that can inform your sketch of the graph as well. Thirdly, we might want to know where the function cuts the coordinate axes. So what the value of the function evaluated at x equals 0 is. That's where the function crosses the vertical axis, and any solutions that there are to f of x equals 0, where the function will cross the horizontal x-axis. We'll want to be able to pick out any asymptotes of the function. So these are lines or other curves to which the function approaches or gets closer and closer to as x tends to plus or minus infinity. Then, recalling back what we did last week, we will want to identify any stationary points in the function. Okay, these are going to be local maximums, local minimums, or points in inflection. It's good to get those located correctly and their nature depicted correctly in your sketch of the graph. Okay? And then finally, having assembled all those bits of information, they kind of give you the main features of the graph of the function, and then it's a kind of a join the dots exercise to kind of sketch out what the curve might be looking like. But just to make sure that at least you've got the information correct about whether the function is positive or negative in various parts of the domain. And whether it's approaching any asymptotic lines or curves from the right direction, whether it's approaching them from above or from below. Okay, so those are the kind of features we look for. So let's take this example and pick out those various bits of information for this example. So this is mostly on the notes. I might add in one or two details just on the pen and paper. So first of all, addressing that first point, is this a well-defined function everywhere? Well, yes, except for the one point where the denominator expression 2x plus 1 is 0. So that happens at x equals minus a half. So that formula doesn't give a well-defined value when x is equal to minus. So, properly speaking, for the domain of the function, we should exclude that point. So this is the set difference here. The real number is less the point minus a half. Okay, so the function is the domain of the function is that subset of the real numbers. Okay, so exactly what is the function doing when you get close to minus a half? Well, when you get close to minus a half, what is the numerator doing? See, the numerator is always going to be close to, when you square minus a half, you get a quarter. And if you're either side of minus a half, when you square it, you're always going to be close to plus a quarter. So the numerator is going to be close to 3/4 minus 7. So that's going to be a negative number. So the numerator is close to a negative constant, which is 3/4 minus 7. But the denominator kind of changes behavior. When you're close to minus a half, but less than minus a half, then the denominator 2x plus 1 is close to 0, but on the negative side. 2x plus 1 is going to be a small negative constant. Whereas if you're close to close to minus a half, so reading here now, on the other hand, if you're close to minus a half, but greater than minus a half, so just close to it on the positive side, then the denominator, again, is going to be close to 0, but it's going to be close to 0 on the positive side. It's going to be very small, positive. So that means as you're approaching minus a half from the right, on the positive side, the values the function is taking on is something close to this 3/4 minus 7. So that minus number divided by something very small and positive. Okay. So that's going to give you a very large negative number. Large in absolute value negative number. So you're dividing a negative quantity close to 3/4 minus 7, divided by something very small, but on the positive. Whereas when you're getting close to minus a half on the left-hand side, so close to minus a half on the negative side, then you're dividing that negative numerator by something very small, which is also negative. So you're doing negative divided by negative, so you're getting something positive. Something that's going to be very large and positive. So you're dividing something close to this constant by something very, very close to 0. Okay. So to summarize, as you're approaching minus a half on the positive side, the function is tending to plus infinity. When you're approaching minus a half on the negative side, the function is approaching plus infinity. And when you're approaching minus a half on the positive side, then f of x is going to be approaching negative. Then we're looking at axis crossing points. You can find those fairly easily. F of 0 is minus 7. You substitute 0 into the formula, so it crosses the y-axis at minus 7. F of x equals 0. So when is f of x equal to 0? F of x is equal to 0 when its numerator is equal to 0. And the numerator, 3x squared minus 7, we can solve that easily. That's got these two roots, plus and minus root 7 over 3, which is approximately plus and minus 1.5. Okay. Then we come to identifying what the asymptote of the function is. And this is something where I might want to just add a little bit of detail to what's there in the notes. So we're looking at this function f of x, which is 3x squared minus 7 over 2x plus 1. So there, you see, as x gets very large, because it's a quadratic, x squared divided by a linear term, just something x. As x gets very large in either the positive or negative direction, the numerator is going to dominate, and so it's going to get very large in absolute value. But we can get an idea of what its tendency is, what kind of curve it's going to be acting like for very large x. If we attempt to divide out 3x squared minus 7, to divide it as much as we can by the denominator polynomial 2x plus 1. Okay, so if you take this 3x squared minus 7, what I attempt to do is write it as some multiple of 2x plus 1. And there's various, so what we're effectively doing is doing long division with polynomials. You may have learned a technique for doing that, setting it out on the page, much like long division of numerical quantities. Or you might not have learned a kind of systematic way of doing it, but you can do it kind of bit by a kind of a piecemeal fashion. And first of all, I'll look for the x term. So you think, well, you see, if I want to multiply this thing, which is order 1, and to get an order 2 term, I must multiply it by something order 1, something involving x. And if I want to achieve that 3x squared, I need to multiply it by 3 over 2x. 3 over 2x will, when multiplied by 2x, the 2's cancel, so you get 3x squared. But of course, you also get, when you multiply it by the 1, you get 3 over 2x. Well, I don't see a 3 over 2x there. So I should subtract 3 over 2 times x in order to complete this equation. So I started off writing an equation. And I still don't have the minus 7, so I need to record a minus 7. Now I can add a full stop. Now that equation is correct. The benefit of writing it this way is I'm starting to see the numerator as some kind of multiple of the denominator. And then you can just do the same in order to generate this minus 3 over 2x. Again, I'm looking to multiply 2x plus 1 by something. So I'll have to multiply that by minus 3/4. Where is that x there? Minus 3/4, won't I? If I multiply 2x plus 1 by minus 3/4, I will get this minus 3 over 2x term. And I'll also get a negative 3/4, but I want negative 7. Okay? Negative 7 is negative 28/4. So if I've already got negative 3/4, means I need an extra negative 25/4 in order to complete that equation. So now, because I've got these two multiples of 2x plus 1, I can package those up together. This is 3 over 2x minus 3/4 times 2x plus 1, and with this remainder of minus 25 over 4. I should stop there. I won't be able to do any further division by 2x plus 1, because this is just a constant here. So you'd have to start involving 1 over x's and stuff, but I don't want to get into that. So that allows us to write f of x. So instead of 3x squared minus 7, I've got this expression now. So it's 3 over 2x minus 3/4 times 2x plus 1. minus 25 quarters, and this is all over 2x plus 1. And now I can actually carry out the division indicated by fraction, and I can write this as 3 over 2x minus 3 quarters, so I can cancel the 2x plus 1s, and then I've still got this minus 25 quarters over 2x plus 1. So the benefit of writing it like that is I can now see this curve here. So now we're thinking of the function as being made of this curve here and this remainder curve. So this curve here, which is a line, because it's a linear term in x, the y equals mx plus c, if you like, it's a line. So this is an asymptotic line. And this is like some kind of error term, but the beauty of it is that it converges to 0 as x goes to 0. So it's a constant over, sorry, as x goes to infinity. It's a constant over 2x plus 1. So as x gets larger and larger, this error term, which measures the error between f and this straight line, this is disappearing. So that means in our sketch of the graph of f, we should indicate the presence of this line on the sketch as well. And as we get further away from 0, it should be that our graph of f is getting closer and closer to this line. Okay. The error between the two is measured by this quantity, 25 over 4, which is approximately 6. 6 over 2x plus 1. Yeah. So I'll just return back to the notes. Just give you a minute to finish getting that down. So returning to the notes at the top of page 55, we then go on to address the next point, which is does the function of any stationary points. Okay? So stationary points, remember, are located where the derivative of the function vanishes. So you can see at the top of page 55 there, when we take the derivative of the function, okay, we have to use the quotient rule for that. So you've got the denominator squared, and then the product rule-like expression, but with a negative sign between the numerator and denominator there in the numerator of the derivative. When you tidy up the numerator, it comes out as this polynomial 6x squared plus 6x plus 14. Now the stationary points are located at the zeros of that derivative dx. So when is this fraction here equal to 0? It's equal to 0 when its numerator is equal to 0. Okay, but when you look closely at that quadratic equation, you realize it doesn't have any real zeros. Okay, because it's 6x squared plus 6 times x plus 14. If you look at the discriminants of that, the b squared minus 4ac quantity, that's a negative quantity. So that means that numerator polynomial doesn't have any real roots. So that means the function doesn't have any return points. So it never goes through a local minimum, a local maximum, or a point of inflection. Okay. So finally, then, you know, we can put all these pieces of information together to produce some kind of a convincing sketch of the graph. And there's a picture of it in the notes, but it's not too hard to appreciate how, by just taking all those pieces of information that we accumulated there, we can draw a sketch of it. So we have the function going through, cutting the x-axis at approximately plus and minus root 7 over 3. Which is approximately 1.5. very roughly. It cut the, so that's 1.5, 1, 2. So somewhere down here, we're drawing equal scales on the two axes, on the x and y axes. Somewhere down there would be the point -7. This is where the curve is cutting the y-axis. That asymptotic line we talked about was the line 3/2x minus 3/4. So that has an intercept of minus 3/4. So it cuts the y-axis at this point minus 3/4, and it's got slope 3/2. Slope 3/2. So when we progress 1, it will have gone up 1.5. So 1 to 3/4, so it will go up to there. So it's some kind of a line like this. So we can put this in some kind of a faint feature on your graph. So this is the asymptotic. This is the asymptotic line for the curve for the graph. And also there's another kind of asymptote at the point -0.5. -0.5 is up here. This was the vertical asymptote for the function. So as you got closer and closer to that line, the function was getting closer and closer to plus or minus infinity according to what side of the line you approached. And lastly, by looking carefully at this expression for f of x involving the asymptotic line, we can figure out which side of the asymptotic line the function is. You see, because for large positive values of x, when you come out here, this error term is going to be -25/4/2x plus 1. So when x is getting very large in the positive direction, that's going to be a very small, that error term will be small and negative. So f of x is equal to the corresponding point on the asymptotic line minus a little bit. So that means the curve will be approaching the asymptotic line from below for large values, for large positive values of x. For large negative values of x, f of x is going to be the point on the asymptotic line plus something very small. So when x is very large and negative, then both the numerator and the denominators are negative, so that the overall error term in that green box there, including the leading minus sign, that will be a small positive quantity. So that means the function will be lying above the asymptotic line. And putting all these items together will indicate some kind of a curve function. Some kind of curved function like this. So you indicate it getting closer and closer to this asymptotic line here, getting large negative absolute values when you go close to -0.5 on the right. And we got some kind of similar behavior here. It won't win any art prizes or anything, but at least we're able to sketch out the main features of the graph and get a good general impression of what it might look like. As I say, this kind of thing has been mostly superseded through the advent of good computer plotting software, but it's still a useful skill, and it will still come up as being useful about how to pick out these main features of the function from the formula. Okay, and we consider it to be an application of the derivative because the idea of locating stationary points is included there. Okay, so the last topic in this chapter then is the section on kinematics in 4.10. So kinematics is the name given to kind of a simple modeling procedure for the motions of bodies. motions of objects. Without too much specific detailed reference to like the physics or the forces that are going on. But just being able to track the motions of things in terms of their position, velocity, and acceleration. And so the reason this is concerning the derivative and integration is that the relationship between these three fundamental quantities of position, velocity, and acceleration is through the derivative, or if you like, through integration, depending on which direction, through these three quantities you're talking about. So we're going to be studying the motion of objects just in a single dimension. So just objects moving, not necessarily in a straight line, but we're just going to track its location according to one dimension. So most of these things will have a basic quantity x of t, and x of t is going to measure the position of the object at time t. V of t is going to be its velocity at time t, and a of t its acceleration. Okay. And the relationship between these three quantities, their definitions, if you will, is through differentiation. So velocity is the rate, is the derivative of position. So that's the definition of velocity. It's the rate of change of the position of something. And acceleration is in turn the rate of change of the velocity. So the acceleration is the derivative of velocity. Now, you may have seen this before, and often when people encounter this before, they learn a whole bunch of what are called Zubat Operations. You may have seen them. Does that ring a bell for people, the Zubat Equations? A bunch of, so typically S, U and V are used for velocities, A acceleration, T is time, and S is sometimes used for displacement or whatever. So sometimes people learn a whole bunch of these different equations for using in different situations depending on which pieces of information you have. But I'd like to propose that learning a whole bunch of separate equations isn't really a clever way to go about it. It's much better to just remember the fundamental idea of the relationship between the three quantities, and then being able to regenerate whichever equation you need depending on the situation. Okay? Because the danger with trying to remember a whole bunch of equations is that in various locations in the equations there are positive and negative signs. And because the danger of trying to remember something that's got a mixture of positive and negative signs is that you misremember it, or recall it incorrectly, or apply it incorrectly. So on much safer ground if you're operating from just a minimal kind of core set of principles that you're not going to make a mistake. And so I believe that these two relations, where velocity is the derivative of position and acceleration is the derivative of velocity, you're less likely to misremember or misapply those. So more likely to produce correct analyses. So there's a bunch of questions in the end of chapter exercises, and there's some examples here which we might take a look at. Showing some example problems and solutions of them. But there's a lot of chatter. These rooms are designed so everybody can hear each other clearly. So I'm hearing an awful lot of chatter. So can we just keep it down, please? Thank you. So if you look at question 1. Question 1 here says a car waits at a traffic light. I mean, this is quite a simple application. The car is waiting at a traffic light and the light turns green. The car accelerates at a constant rate of 6 meters per second for 4 seconds. What velocity will the car have reached after 4 seconds, and how far will it have traveled? So quite often a little sketch is maybe a good idea to illustrate these things. Here's the car at the traffic light. Indicate the positive direction of your x-axis. It makes sense to place the origin of the axis at the starting position of the object, and we'll begin at time 0. So at time 0, the car is located at position 0. So i.e. x at time 0 is equal to 0. The position of the thing is time 0. And you're also told in the question there that the car is waiting at the traffic light. So its initial velocity, when the light turns green, the car is stationary. So its initial velocity is 0. On the acceleration, we've got a constant acceleration, we're told. So a of t is always 6 meters per second per second. So, now what's it asking us to find? What velocity will the thing have reached after 4 seconds, and how far will it have traveled? Well, if we want to know its velocity at 4 seconds, we need to know the function v of t. The function v of t is defined as the the integral of acceleration. The integral of the acceleration. This is just the integral of the function, constant function 6. So v of t as a function is equal to 6t plus c. You have a constant of integration. And what exactly is this constant of integration? This constant of integration, of course, is equal to v of 0. So if you put in t equals 0 here, that cancels out that term, and you have the constant c equal to v of 0. And we know what that is. We know v of 0 is equal to 0 because the thing is starting from rest. So that means our velocity function is 6t. And we also need the position function, x of t. X of t is defined as the integral of velocity. What's the integral of 6t? Which is what? 3t squared, again, plus a constant of integration, d. But again, this d, this constant of integration, is equal to x of 0. You see that by simply putting in t equals 0. And part of the setup of the problem, the way we set it up, was that x of 0 is equal to 0. We're going to begin the car at position 0. So the required information, the information we were asked for, is v of 4, the velocity it reaches after 4 seconds, which is 24 meters per second. It's just 6 times 4. And its position, that's pretty fast, 24 meters per second. To 100 meters in 4 seconds. Not too fast for a car, I guess. Its position is x of 4, which is going to be 3t squared, so 3 times 16, 48 meters. So it will travel 48 meters after those 4 seconds. Okay. Any questions about that? Yes.
Is that ms-1?
Yes, meters per second, because that will be the units of velocity. If the units of acceleration was meters per second, you can integrate that with respect to time. It'll change the units up to.
Why does it -1 meter?
No, it's meters times seconds to the -1. So meters per second. Yeah, yeah.
And what's the arrow at the very top? Yes.
That arrow there, I was just indicating the positive direction of the x-axis, which is normally from, as you move right, you move through positive values. Just kind of indicating that that's the direction of travel. Second question is a bit more detailed in that we've got 2 things moving. So this imagines a student who's running to catch a bus. And where we enter the situation is the student sees the bus start to pull away from the stop. So here's the bus stop. Here's the bus. at position 0, let's say, and the bus is starting to pull away, it's starting to move in this direction, and the student's running to catch it. He's 20 meters away from the stop and running at his top speed of 5 meters per second. So if he's 20 meters away from position 0, it means he's back here at minus 20. The student running to catch the bus. This is where we see it. The bus is starting to pull away, so it's at position 0. It's starting to move. He's running at his top speed of 5 meters per second, so he's going that way at 5 meters per second. It's his top speed, so he's not going to get any faster. The bus is accelerating at 2 meters per second per second. The bus is accelerating at 2 meters per second per second. So the question is, can the student catch the bus? Maybe he will, maybe he won't. So there's two bodies here, so we're going to need two sets of quantities to represent them. So if we let xs, bs, and as be the student's quantities, position, velocity, acceleration, and xb, bb, ab be the bus's position, velocity, and acceleration. And the question, provides us various bits of information. So the first thing to do would be to just make note of, which bits of information we have. The position of the bus at time 0 is 0. We're going to choose that as the origin. Position of the student at time 0 is minus 20. The student is 20 meters away. The initial velocity of the bus, well, the bus was waiting at the bus stop. So time 0, when we first see this, the bus is stationary, it's just beginning to move. And the acceleration, and it's got a constant acceleration of 2 meters per second per second. The student is running, and the question says they're running at their top speed, the top velocity. So if that's their top velocity, they won't be getting any faster, so acceleration is 0. In fact, the acceleration for all reasonable t, so as long as the student can keep going at their top speed, their acceleration is going to be 0, and we'll assume v of t is always equal to 5 for all reasonable t, for some reasonable period of time that they might be able to keep their top speed going. Depends how fit they are, of course. But there you go. So mathematically what we're trying to solve is, are there solutions to the equation, the position of the student being equal to the position of the bus? That's basically what we're asking. If the student can make it to the back of the bus on time, we're thinking of those old-fashioned London-style buses where you can hop on at the back when the thing is moving. Yeah, I guess that's part of it as well. But those old-style buses where you could actually jump onto the moving bus if you were so minded. Any solution and any solutions in positive time, because the setup that we set up will probably allow us to run time backwards, and maybe they would meet then, but we can't do that, so we have to just go for positive time. So we need to know what the position of the student looks like at time t. So this is the integral of the student's velocity. Well, we told the student is at their top speed of 5 meters per second per second. So this is the integral of 5 dt. So this is 5t plus a constant. But the constant is going to be, of course, the initial value of x, which is going to be minus 20. This is 5t minus 20. the velocity of the bus at time t will be the acceleration, sorry, the integral of acceleration, which is the integral of 2, integrating with a constant constant acceleration 2. So this will be 2t plus the initial value of dv, which is 0. So the velocity of the bus at time t is 2 times t. So the position of the bus at time t is going to be the integral of its velocity, the integral of 2t, which is going to be t squared plus some constant, which is the initial position of the bus. And the way we've set it up is the bus begins at the origin. So the initial position of the bus is 0. So the position of the bus is just t squared. So they have these nice expressions now for x of s, 5t minus 20, the position of the student, and the position of the bus, t squared. So are there solutions to the position of the bus being equal to the position of the student? Well, that's just a quadratic equation. T squared minus 5t plus 20 equals 0. But again, if you assess this quadratic equation, if you look at its discriminant, b squared minus 4ac, b squared is 25, 4ac is 80, so it's got a negative discriminant. So again, no real solutions. Okay. B squared minus 4ac is a negative quantity. So the student cannot catch the bus. We might ask, could any student have reasonably caught this bus? Was it just too far away? You know, is it impossible to catch a bus that accelerates at 2 meters per second from 20 meters distance from you? Obviously, this student isn't fast enough, but could any student be expected to catch this bus? We answer that question. So the reason this student couldn't catch it because this quadratic had no solutions. Now, where is the when you track through the analysis? Where is the velocity of the student somewhere in this picture? Yeah, this 5 here is the velocity of the student. This was the quantity b of s. So the discriminant, if everything else was the same, the bus is still accelerating at 2 meters per second, the initial separation is 20 meters, then the discriminant is b squared, so it's bs squared minus 4ac minus 80 equal to 0. Sorry, minus 80. That's the discriminant, b squared minus 4ac. And the first time, so there are no solutions when this is negative. So the first time that there are solutions to the quadratic is when the discriminant takes on a 0 value. So this is equal to 0 if and only if the velocity is the square root of 80, which is well, 80 is 4 times 20, so it's going to no, 80 is 16 times 5, so the 16 has a square root of 4, so that's 4 times root 5, so that's approximately 8.94 meters per second. So if the student had been running at a velocity of 8.94 meters per second and was able to maintain that, then they might have caught the bus. Now, how fast is that? Is that a reasonable speed? This is equivalent to this average speed is equivalent to covering. It's easy to just get an idea of how fast that is to think how fast will they cover 100 meters. So that is covering 100 meters at 11.18 seconds. So is that, anybody in this room do 100 meters in 11 seconds? It is, but it's not beyond the realms of, that's a reasonable college sprinter, I'd say. A reasonable young athlete. Sorry?
Yeah.
11.18 seconds. 11.18 seconds. So just over 11 seconds. So maybe for a good sprinter. Okay, so there's lots more questions like that in. Well, there's one more example there in example 4.12, and there's more such questions in the end of chapter exercises. So there's plenty of things to practice with there in the tutorials. I might look at a few of them next week as well. So other than that, I'll leave you there for this morning. So keep your eyes out to your email. I'll send around the announcement by email when the mock test is up.